Catherine, can you stop the sharing for a minute, please? Thank you. Jeremy, it's still the 20-second video. I'm not sure what it means, but again, I still don't see anything on the YouTube thing. Not on my end. Okay, I'm recording it on Zoom anyway, so let's just go ahead, and worst case scenario, we will just upload that video that we're recording on Zoom, and then we can go from, and I will post the link to everybody so they can watch it. It's a remote thing anyway. You want to do that? All right, ready? All right, good evening, everyone. We're having some technical difficulties, so there's a slight chance that you will not see this live, but only the recorded version of it. If that is the case, then I apologize. If that is not the case, and I'm not aware of it, then I apologize. And in any other case, I will not apologize. I received a few emails from you after the announcement today, whether when will we be back on back live in the auditorium. Please trust me when I say we would like nothing else better than to go back live, because it's just not the same doing this, not just for you, but for us as presenters or hosts. It's significantly better and significantly different to be in the same room with you, and we would like nothing better than to do just that. However, at this moment, the university did not authorize going back into a live version. As soon as that will happen, we will be more than happy to host you. So for today, we will have a remote lecture, and the presenter will be Dr. Neish from Western University. Dr. Neish received her bachelor degree in physics and astronomy from the University of British Columbia, and then her PhD in planetary sciences from the University of Arizona. After a postdoc stint, she was actually at Florida Tech in the very office that I'm talking from right now, in the very chair at the very desk. And after that, she went home to Canada, and since 2015, she's a professor at Western University. Her research area is focusing on geology of planetary surfaces, in particular impact cratering and orbital radar observations. She was a member of she is the Lunar Reconnaissance Orbiter, and she was also a member of the Cassini team, in particular the radar team that was focusing on Titan. And today she is going to talk about the Dragonfly mission to Titan, my apologies. Dr. Neish, floor is yours.
Thank you very much for the warm welcome, and hello everybody. I was looking at the temperatures in Melbourne before this talk, and I think it's about 30 degrees Celsius colder here in London, Ontario. So I do like the snow, though. It is very fun to go skiing and skating. And another place that is quite cold that I'm going to be talking about tonight is Saturn's moon, Titan. Chubb, are you seeing my screen?
Yes, I do.
Excellent. Okay. So Titan is Saturn's largest moon. What just happened? And it is also my favorite place in the solar system. So I'm going to tell you a little bit more about Titan tonight, and the exciting new mission we're planning to send there in the coming decade called Dragonfly. So this image here that you're seeing is a beautiful image taken of my favorite place in the solar system, taken by the Cassini mission during its lifetime. So Cassini operated around Saturn from 2004 to 2017, taking a number of incredible images and collecting lots of data that told us more about Saturn, its rings, and its moons. So I told you this is showing you a picture of my favorite place in the solar system. And you're probably thinking I'm talking about Saturn. And this is, of course, a beautiful image of Saturn. But really the place I'm talking about is this sort of inconspicuous orange dot sitting right here in the ring plane in front of Saturn. And this is Saturn's largest moon, Titan. And when you look at the large moons of our solar system, Titan really stands out. So not only is it one of the largest moons in the solar system, just shy of the size of Ganymede, which is Jupiter's largest moon off here to the left. But when you look at the other moons, you'll notice that they're almost entirely airless, except for Titan. Titan is the one moon in our solar system with a large, thick, complex atmosphere. And this really makes it stand out for a number of reasons that I'm going to get to. It makes it a very interesting target for studying geological processes, but also the origin of life. And that's really what we're keen on looking into more with Dragonfly. So how do we know what we know about Titan? Well, we've been very, it's been a great honor to have two spacecraft visit Titan and return data from that world. The first was a while ago, the really famous Voyager spacecrafts from the late 70s, early 80s, flew by Titan in 1980 and collected some really incredible data about its atmosphere. And then this was followed up in 2004 with the Cassini-Huygens mission, which was a joint NASA-ESA project. So NASA provided the orbiter, that's Cassini, which you see here. And then there's this orange disk off to the right, which is the Huygens probe, which touched down on Titan in January of 2005. So just about 17 years ago, and returned images from Titan, from its atmosphere and from its surface. This is the farthest we've ever landed on any object in the solar system, was Titan. And we're gonna do it again with Dragonfly. So what did we learn from these missions? So I mentioned that Voyager flew by Titan in 1980, and this is one of the images it returned. In fact, we knew so little about Titan at the time that Voyager was not equipped with any camera that could see the surface. And so this was the only image we had of Titan. Fortunately, it did have many other instruments that taught us a lot about its atmospheric structure, its composition. We learned that Titan has a lot of methane in its atmosphere, which is incredibly interesting for organic chemistry. And we learned how big Titan was. Up to this point, we actually didn't know where the surface started and the atmosphere began. And so it wasn't clear up to this point what the largest moon in the solar system was, whether it was Ganymede or Titan. But as I mentioned, it fell a little bit shy of Ganymede, and so it's the second largest moon. So we learned quite a bit from Voyager, but we never saw the surface. It wasn't until 2004 when I started grad school at the University of Arizona that Cassini arrived equipped with the appropriate cameras to see the surface. And so Titan went from this mysterious orange orb to a whole new world that surprisingly turned out to be very Earth-like in appearance, which you wouldn't expect for a large icy ball out around, orbiting around Saturn. So we learned quite a bit about Titan over the 13 years of the Cassini mission, but there's a lot more we need to know. So we are going to send a new spacecraft there to learn more. And just to give you a brief overview of what you're seeing in this image, this is an infrared image of Titan taken by the Visual and Infrared Mapping Spectrometer aboard Cassini. Here at the north and south poles, you're seeing these bright plains. We're still not entirely sure what they're made out of. They're these very curious bright regions. At sort of the top Middle off to the right here is an impact crater, probably the freshest impact crater on Titan, called Sinlap, and it has this beautiful ejecta blanket, and we see ice coming off here to the left. And then this orangish brown material that circles the equator are sand dunes. So I'm going to show you close-up images of all of these features here. So what have we seen of Titan that makes it look so Earth-like? Well, the first thing we noticed is it has weather. So like Earth, Titan has a hydrological cycle, except it's not made of water. Titan's surface temperature is 95 Kelvin. It's about 200 degrees below the freezing point of water. So these are not water clouds. What's liquid on Titan is actually hydrocarbons. So we're talking methane and ethane. It's like having gasoline rain out of the sky, essentially. And so that's what we're seeing in this image here. This bright feature near the equator is actually an enormous cloud that came and rained on the surface, and we actually saw the surface darken from the rain and then brighten again as it dried out. So this is quite amazing. What does this do to the surface? Well, it forms stream channels. This is an image taken by the Huygens probe as it was floating down to the surface through the atmosphere. And if I hadn't told you that this was of Titan, you know, it might look like any image you might see staring out an airplane window, perhaps you know, some dry river valleys in California or Arizona, coming down from these highlands, these river channels into perhaps an ancient riverbed here. And this is where Huygens eventually landed. And we saw cobbles that seemed to indicate that there had been moving liquid here at some point. But this is small potatoes compared to what we see at the poles. So what you're seeing here is the North Pole of Titan. It's that black dot, it's sort of center right. And here we see these enormous lakes and seas of liquid hydrocarbons. So these are about the same size as the Great Lakes on Earth. So I live squished between Lake Huron and Lake Erie, and these are similar in size to those features. But they're not made of water. They are made of primarily methane, we think, forming these enormous lakes, huge river valleys connecting them. So really fascinating features. And though this is colored, this is really a radar image that we're seeing here. So these colors are not real. But what you can see is that the lakes themselves are very, very dark. And this indicates that they're incredibly so we're seeing very, very smooth bodies of liquid. And we can actually probe through the liquid to the bottom and get depths for these lakes. And some of them are 100 meters or more deep. So this is enormous reservoirs of methane on Titan. And this is interesting. If you're interested in sort of weird life, you could imagine life maybe existing in a different solvent than water. You know, could life exist in these lakes of methane? Would that be a potential place for the origin of life? So how do we know that they're lakes? Well, in addition to them being very flat at the radar wavelengths, they're also incredibly flat at optical wavelengths. So this is another VIMS image of Titan. And what you're seeing here, that bright dot at the top of the image is a specular glint off a lake near Titan's pole. And so this is something you're probably very familiar with on Earth. Again, let's say you're looking out that airplane window, the sun is setting, and you notice a glint coming off a river where the sun is perfectly aligned to bounce off the river, and that light goes right into your eye. So this is very common when you have a very flat surface, and we see evidence for this near the poles of Titan. Earlier, I showed you a global image of Titan with those brown sand dunes. Here's a close-up image of those dunes. You can see they're very long. They go on for hundreds, thousands of kilometers around the equator of Titan, spaced by a few kilometers. And Titan has more sand dunes on it than any other world in the solar system, which is not something we were necessarily expecting. But this sand is very different than the sort of sand you might find at the beach there in Melbourne. This sand is made up of organic molecules, not the silicate sand we see on Earth. So it's really, quite a hazardous beach to go to. These compounds are probably quite carcinogenic. So we call them sand because they're the right size to be sand and therefore get picked up by the wind and blown into dunes. But it doesn't necessarily mean they're made of the same stuff as we see on Earth. So Titan in many ways is like this bizarro Earth where you see the same features, but all the ingredients are wrong. And then almost lastly, and most speculatively, there's thought there might be volcanoes on Titan. And this is probably our best example. This is called Doom Mons after the Lord of the Rings trilogy. And then we off to the going up here, we see Mohini Fluctus, which looks an awful lot like a lava flow. Going off here to the north, we see a tall mountain, perhaps a caldera. But what's weird about a volcano on Titan is that since it's made of ice, any lava you have would be water, right? So on Earth, we melt the rock to make silicate lavas like basalt. But on Titan, if you melt the rock, you're just going to get water. And this is actually a really tricky thing to do because as I'm sure everyone is aware, if you put ice in water, it will float. So how do we get liquids up and over this icy shell onto the surface? It's not well known how this happens, but it seems like it could be happening here on Titan. And we call this cryovolcanism or cold volcanism. And it's something people are interested not only on Titan, but elsewhere in the outer solar system. And then lastly, here is a close-up image of the crater I showed you earlier on that global view of Titan. This is a radar image. So we're seeing the very rough ejecta making the radar signal very bright surrounding the crater. And then off to the left here, you can see those sand dunes again creeping up on the crater. Eventually they will overtop the ejecta and fill in the crater. And we see this for more degraded craters on Titan. But this is my favorite feature on Titan. I've spent my career studying impact craters on Titan. And one of the reasons I like them is because, like cryovolcanoes, you can find liquid water here, at least for a short period of time. When a comet strikes the surface and makes this big hole in the ground, it also tends to melt some of the surface. So again, we're going to have liquid water present on the surface. And when you have liquid water on the surface and you can mix it with those organic sands we find nearby, there's a possibility you could have an origin of life very different to the one that occurred on Earth 4 billion years ago. So to summarize what we know about Titan, we call it an ocean world, and it has an organic rich atmosphere. And when you mix those things together, it makes it a prime location to study the origin of life and potential habitability elsewhere in the universe. So I'm going to explain more about this organic rich surface, but to tell you more about what I mean by an ocean world. So Titan, as I mentioned, is made of ice primarily with a silicate interior. That's what you're seeing here in green. And it turns out that ice, if you increase the pressure and the temperature, it will turn back into water before eventually turning into higher pressure phases of ice. And so you get this sort of water sandwich between two layers of ice if you have a large enough icy satellite. So we think many of the icy worlds in our outer solar system, including Titan, but also Europa, Ganymede, and others, have this subsurface ocean, which is also incredibly interesting for astrobiology. If you get the organics on the surface down through this crust to the ocean below, that would be another prime place for the origin of life to occur. So we want to go there and learn more about it and see if we can study more about these prebiotic processes happening there. But in addition to water, right, we also need organics. And so Titan is pretty unique in the fact that its atmosphere, its large atmosphere I was referring to before, is made up primarily of methane and nitrogen. It's about 95% nitrogen and 5% methane. It varies somewhat within the atmosphere though. And what's cool is if you bombard this with ultraviolet radiation or charged particles, you end up making a whole suite of more complex organic molecules. Things such as ethane and acetylene, hydrogen cyanide, and so on and so forth. Basically, if you can think of a way of putting carbon, hydrogen, and nitrogen together into a molecule, it probably exists on Titan. So this is really a great place to where you have the building blocks of life already and waiting in the atmosphere and on the surface to perhaps kickstart an origin of life if you only get it access to water. So to summarize, Titan is really a great place to study prebiotic chemistry and the origin of life because it has all the elements we think we need for that to occur. So we have carbon, hydrogen, nitrogen in the atmosphere. If they mix with water, you can introduce oxygen. The only things we're really missing are phosphorus and sulfur. It's unclear how much of these two elements are present on Titan. So this is something we're hoping to learn more about with Dragonfly. We have energy available too for life in the form of solar energy, but also internal energy from Titan itself. And then not only do we have potentially water sources in the form of volcanoes and impact craters, we also have these methane lakes. So we have two different possible solvents for life on Titan. So it really is a fascinating place to look for life. So just to reiterate, here are the two solvents that we're interested in on Titan. We have these methane, ethane lakes near the poles. If we were to look for life there, we'd have to be very creative because this life would be very different than what we find on Earth. To have a life operating in a non-polar solvent at 95 Kelvin would be quite a task. I'm not convinced there is life in these lakes. It would be just so slow. Reaction rates drop off very quickly when you start to lower the temperature. So that is my biggest concern about life in these lakes. So I focus most of my effort on understanding the sort of life we could get in these transient water environments. So I mentioned you could get water on the surface in volcanoes and also through impact cratering processes. Eventually this water will freeze because Titan is very cold. We don't know exactly how long that will take. It might be hundreds or thousands of years though, which gives us a good head start in sort of the process along the path to life. So we're interested in studying craters like this to see, on timescales much longer than you could look at in the lab, what sort of products you could make when you mix the organics on Titan surface with this liquid water. And it might create something like life as we know it here on Earth. So this was something that I studied in my PhD at the University of Arizona. So I got to do some lab work, which was really fun. And so what I did is I took Titan atmosphere simulations, so methane and nitrogen, put them in a glass tube. I sparked them with some energy, and then you let this sit for a couple of days and you form this sort of brown sludge that Carl Sagan termed tholins, which comes from the Greek word for muddy, because they look kind of brown and muddy. They are horribly toxic though, because again, you're making all these carbon molecules, some of which are very carcinogenic. So I had to be very careful when I was handling these. But I took these organic organic mud, and placed them in liquid water and left them to react with the water to see what they would make. And I found that if you left them long enough, you could actually make biological molecules like amino acids. So we made, I think, about 7 of the 20 amino acids that are used in life in this experiment. How do we know we had those molecules? I'm going to show you some of the data that we collected. This was in a lab at Goddard Space Flight Center in Greenbelt, Maryland. So the first thing we did is we put some standards in our mass spectrometer. So the 3 simplest amino acids are glycine, alanine, and serine. And so these are just standards you could buy from the store. We definitely know these are the correct amino acids. And then you find peaks at very characteristic points on this axis, and then we can compare them to our sample. And if you split back and forth, you can see that the peaks in our sample line up with the peaks from the standards. So we were pretty convinced that we had found these 3 amino acids, which was pretty exciting. And I was also amazed at just how easy it was. You just take some methane and nitrogen, you spark it, you put it in water, wait a little while, and you can form amino acids. So this gives me hope that it's actually quite easy to start life if it's this easy to make amino acids. I also did some work on their reaction rates and found they were quite fast. Some of these reactions, took hours or days to complete at Titan relevant temperatures. So you can make amino acids and you can make them in timely fashion. So I'm convinced that we're going to find amino acids in an impact crater on Titan when we send Dragonfly there. And so I was very hopeful in my PhD when I was writing this up. So this is the last page of my dissertation, which I submitted in December of 2008. And I'm going to zoom in on the final paragraph here, which reads, plans for a new NASA flagship mission to Titan are currently underway. If selected, this mission will provide new insight into the process occurring on Titan's surface. Titan has been conducting natural experiments in prebiotic chemistry for eons. Now all that remains is to collect the results. So I really wanted to go to Titan and see the amino acids being made there on the surface naturally. And at the time, NASA was looking into sending a flagship mission, which is one of their more expensive billion-dollar class missions to Titan. But we needed the support of the scientific community and NASA to make this happen. So a few years later, the planetary community came together and wrote what we call the Decadal Survey. So this was supposed to dictate the priorities of planetary science for the decade from 2013 to 2022. So you'll notice it is now 2022 and they're writing a new decadal survey, but this is the document that's been guiding our exploration of the solar system for the past decade. And so I was really hoping to see Titan in this document, so we would have some support to return there and look for some of these interesting molecules I had created in the lab. Unfortunately, my dreams were somewhat crushed when this was released. So here is one of the tables from that document. It's a bit of an eye chart. I'll point out the relevant things, but you'll see at the top here, we have recommendations for flagship missions. And then near the bottom, we have recommendations for New Frontiers missions. So this is a slightly cheaper version of a flagship. The catch is that you can only propose to do certain things. So there's like a list of 5 missions you can propose to do. And if it doesn't fall into that mission, then you can't propose it. There's another class of mission called discovery missions, which are just not enough money to send a mission to Titan, really. So let's look at the flagship missions. What did they recommend? Well, they recommended a Europa orbiter. So Europa won over Titan. And in fact, this mission is now in preparation. It's called Europa Clipper. It turned out not to be a Europa orbiter. It's a Jupiter orbiter because it's really, really hard to orbit Europa because of the radiation environment found there. But Titan flagship mission was voted number 2. And so they were not going to fund that as a flagship mission in the past decade. And then we look at the New Frontiers mission. And if you read all the different options for that, Titan was not in the list. So I ended my PhD on a high note and then realized we probably would never be going back to Titan in my career. So that was sort of depressing. And I started a postdoc looking at lunar data to sort of diversify my interests. So you can imagine my surprise when in January of 2016, I received this email from NASA. So this is an announcement regarding the next New Frontiers opportunity. So New Frontiers were that sort of medium class mission where you need to fit into one of the targets that NASA had identified. In the decadal survey, Titan did not appear. And yet in this email, suddenly it appeared. I don't know how this happened. There was some sway perhaps from a certain congressman at the time that might have included this. This is not following the decadal survey. This should not have happened, and yet it did. So out of nowhere, we had an opportunity to propose a mission to Titan. And so we did. So colleagues of mine got together to propose the Dragonfly mission to Titan. If you read our Wikipedia page, you will see where the idea came from. 2 of my colleagues, and indeed one of my PhD mentors, Ralph Lorenz, and then my colleague Jason Barnes, basically just sat down and kind of worked it out over a napkin over dinner. Ralph has been involved with Titan exploration for many years. He designed one of the instruments on the Huygens probe, and speculated you could have helicopters on Titan 20 years ago. And then Jason proposed an unsuccessful proposal called Aviator, which would have sent an airplane to Titan. And so they got together and then talked with other people at the Applied Physics Lab at Johns Hopkins University. And it was decided that Dr. Elizabeth Turtle would lead this mission. And so she is the principal investigator of Dragonfly. So what makes Dragonfly different is it is an aircraft. We call it a relocatable lander, but really it's a giant drone with 8 wings that will fly around Titan. Why are we going to fly? Well, on Titan, it's actually easier to fly than it is to rove. So while roving is the easier solution on Mars, and I'm sure you're all familiar with the Curiosity and Perseverance rovers, on Titan, it's actually much easier to get around by aircraft. So we could utilize this really unique platform to tackle these questions around the origin of life that are so interesting on Titan. I will note also, this is a much easier way to get around. In one hop of Dragonfly, we can go the distance that Spirit and Opportunity rovers on Mars went in 10 years. So we're going to be able to traverse quite a bit of Titan in a much shorter time period than the rovers ever could. If anyone here is a fan of XKCD, they have a fun explainer about how you might fly on other planets in our solar system. And you'll see this little interplanetary Cessna crashing on many, many worlds. It's actually amazing that they were able to fly that tiny helicopter on Mars. Mars is a very difficult place to fly. But Titan is actually one of the easiest places to fly in the solar system. And this is what XKCD has to say about it. When it comes to flying, Titan might be better even than Earth. Its atmosphere is thick, but its gravity is light, giving it a surface pressure only 50% higher than Earth's, with air 4 times as dense. Its gravity, lower than that of the moon, means that flying is easy. Our Cessna could get into the air under pedal power. So in fact, having an aircraft on Titan makes a lot of sense. If we had the same Dragonfly on Earth, we'd actually need bigger wings than what we have for Titan. So this was the idea. Let's send this aircraft to Titan to understand its temporality. And we proposed this in 2017. It was selected for launch in June of 2019. We're currently set for a launch in 2027, and then we're planning to arrive in the mid-2030s. So outer solar system exploration takes a long time. This is why I was so pessimistic about seeing a mission in my career when the Decadal Survey said that it wasn't going to happen, because it takes decades to plan these missions and then to send them out into the outer solar system. So, but we're very excited this was selected, and we're eager to see the results from this mission. So what does Dragonfly look like? Here you can see it on the right. We have a director of communication. That's how we're going to talk to Earth. We have instruments inside here, our nice insulated container that will keep us warm and safe. And then we have a radioisotope powered engine here at the back that will power a battery, which will allow us to fly. Here is Dr. Elizabeth Turtle holding one of the wings of Dragonfly to give you a sense of scale. The whole thing is sort of the size of a small car. It's about as tall as I am, and maybe 2 times as tall as I am long. So it's quite a significant piece of hardware. This is part of the Dragonfly team. You can see here meeting to plan our proposal in 2018, just outside Johns Hopkins University Applied Physics Laboratory. And we were testing out a little demo version of Dragonfly. It's now much more sophisticated than this, but this was what we were using for our proposal. So I'm gonna show a little video here in a second of what Dragonfly might look like flying in a fully automated sort of way. don't think I have any sound. But you can see it taking off, and then it's going to fly around this farm field in sort of a square, and then return to us at the other side of the field. So if you just put an orange tinge on this video and get rid of the trees, this might be what we look like flying around on Titan. This is a scale model. The real Dragonfly will be a lot bigger. And we had an operator here just as a fail-safe in case anything went wrong. All right, and now it's starting to land. So we're hoping to see this happening on Titan in about 10 years. And a safe landing. There we go. So where are we hoping to land on Titan? We're planning to land in the sand seas near Selk crater. So Sinlat crater, the one I was showing you earlier, is off here on the right. Selk is here in the middle. It's another large fresh crater on Titan's surface, surrounded by sand seas. And sand seas are a great place to land. So here's Selk crater zoomed in a little bit. We're going to land to the south of Selk crater here in these sand seas. And if you're looking for a nice flat place to land, you can't find anything better than this. So here's what we're thinking it might look like from an Earth analog sort of perspective. You can see some sand dunes off here to the right, and then these nice flat interdunes in between, which make for excellent landing sites. No hazards, a nice sandy surface to land on. And then once we land safely, then we're going to hop our way northward so we can sample that impact melt in Selk's interior and perhaps find evidence for prebiotic chemistry. So what are the goals of the Dragonfly mission? We have three main goals: to understand the chemical components that are needed for biology, to understand the environments you need for life. Specifically, we're looking for these past areas of liquid water where the water may have mixed with organics to form biological molecules. And then very uniquely, many instruments NASA has sent out do not have this capability. We're actually able to search for biosignatures. So these are things like isotopic fractionation, some sort of chirality to the molecules that is unique to life, certain patterns that you would expect for life to take that non-life would not take. We're able to detect these features. And if we find many of these features in our samples, that would argue strongly that there is or was biology in the regions that we're studying. So I'm going to show you a short video now sort of explaining the science of Dragonfly in a bit more detail. So let's, oh shoot, I'm not sure if you can hear it. I might have to do something. Let's see.
Saturn's largest moon, Titan, has a thick atmosphere and a frozen surface rich in organic molecules. In 2034, a NASA mission called Dragonfly will arrive at Titan and study its chemical makeup. Dragonfly is a rotorcraft designed to visit multiple sites across the moon's varied terrain. At each new landing site on Titan's surface, Dragonfly uses a pulsed neutron generator and onboard gamma-ray sensor to detect key elements such as carbon and hydrogen in organic materials or oxygen in water ice. Dragonfly determines if there are well-defined layers of these materials just below the lander. For a closer inspection, Dragonfly uses its drill to generate tailings from Titan's hard, frozen surface. These surface samples can then be ingested through the pneumatic system, carried with Titan air into the chilled sample lines into the sample collection carousel. One of the carousel sample cups is placed in a pneumatic port. The cup captures the surface material from the cold air stream and transfers it to the chemical laboratory for measurement. Pulses from a laser release large organic molecules from the surface sample for analysis in a mass spectrometer. The mass spectrometer sorts molecules by mass and measures diagnostic fragments that tell Dragonfly the kinds of chemical components that are present in the surface and whether there are molecules of prebiotic interest. For those potential prebiotic samples, a new cup is placed into an oven and heated to release molecules into a gas chromatograph, where they are sorted for size and type before entering the mass spectrometer. This advanced separation of organic components includes isolating molecules with the same formula but different chiral arrangements, or handedness. Having a preference for one-handedness over another is a key biosignature for life on Earth. When the chemical analysis is complete, Dragonfly may choose to take another surface sample or find a new location on Titan to investigate.
So hopefully this is what we're going to be doing in about a decade on Titan. I will note that if you want to see these videos and more, we have a lot of great features on the Dragonfly website.
Saturn.
Oops, okay. So they alluded to some of these instruments in that video, but let me just tell you what instruments we have on board. We have 4 main instruments, all with fun dragon-related names. We have DragMet, which is actually a bunch of different sensors used to study meteorology of Titan and also seismology. DRAMS is our real superstar instrument. It's that fancy mass spectrometer that is going to tell us what molecules are present on the surface and whether they have any indicators for biology. And it's coupled with the Draco ingestion system, which is basically a giant vacuum sucking up tailings from the surface and ingesting them into the mass spectrometer. We have a whole suite of cameras called DragonCam to see the environment around us. And then we have a gamma ray and neutron spectrometer, DRAGONS, which will give us broad compositional information about the subsurface. So the DRAMS instrument is modeled after the SAM instrument on Curiosity, if you've heard of that one. And so here's some data from that instrument on Mars. And you can see it was able to detect some organic molecules on Mars using this technique, benzene, for example, over here. And so we're helping to do similar studies on Titan to find organic molecules. DRAGONS, as I mentioned, will give us that broad elemental composition under the lander. So we'll be able to tell if it's water ice or ammonia or something carbon rich in the top few centimeters. What's cool about DRAGONS is we actually get to bring our own neutron generator on board. So most of the time when you have a neutron spectrometer on a spacecraft, you just wait for the heavens to bombard you with gamma rays and neutrons. But this is not an option on Titan because the atmosphere shields them all. So we have to bring our own. And there's actually a company on Earth, Schlumberger, that does this for mining in oil exploration already, because they drop these neutron generators down wells to tell if there's oil present in the subsurface, because there's also no gamma rays in the subsurface. They use a similar technique. So we're able to use that technology now on Titan. DragMet, as I mentioned, is a meteorology package, but perhaps the thing I'm most excited about is the seismometer on board, which will tell us more about the subsurface structure of Titan's ice crust by looking for Titan quakes and seeing the resultant data. And then DragonCam is actually a number of different cameras. Again, similar to what you might have seen on Curiosity or Perseverance rovers. We have panoramic cameras to see the world around us. We have downward cameras to look under the lander, forward-facing cameras, and then the really interesting microscopic cameras to get a real close-up look of the surface of Titan. We also have the capability for night imaging. Titan's day is 16 days long, so we will be in the dark for quite a bit of time, and so we want to have the opportunity to image at night as well. So to conclude this presentation, I want to show you the sequence we have in mind for when Dragonfly will hopefully land on Titan here in the 2030s. You might have heard of the 7 minutes of terror for Mars, where you have that 7 minutes of it diving through the atmosphere. But the atmosphere on Titan is much, much thicker than on Mars. And so my colleagues have jokingly referred to it as 2 hours of moderate concern as Dragonfly slowly settles into the atmosphere. It's a lot safer place to land. The atmosphere really cushions your fall to the surface. So this is what we're hoping that will look like in about 10 years. So eventually the parachute will launch and slow down our trajectory to the surface. So we're now 90 minutes into this. So again, a nice slow descent to the surface of Titan. The heat shield will separate, revealing the spacecraft. And we're actually going to land flying. So as you'll see in a minute here, the rotors are going to start rotating, spinning up, and we're just going to drop down and start flying to our first landing site. And we're quite, like I said, we're confident we should be able to find a safe landing site in this area of sand dunes where there are no obstacles to encounter. But we'll do a little bit of reconnaissance to make sure we found a nice safe spot to land, and then touch down for our first landing site on Titan. So we're really excited to see this data in about 10 years, but all this wouldn't be possible with all the really smart, hardworking people on the Dragonfly team, especially the engineers. I have no idea how to build a spacecraft like this, and I'm so thankful for people who do know how to do that. And so here's the team, and we're ready to go to Titan. And if you have any questions, I'd be happy to answer them now. Thanks very much for your attention.
Thank you so much for the presentation. Let's, in the absence of everybody else, I will cut for you. And I'm pretty sure that people would have questions. So I came up with a few that hopefully covers a number of questions that the audience would ask. And also I can see that Brian has a question, or Brian has a question from Erin, actually. Let me try to get that. Okay, so Brian asks, how long is the time scale that liquid water is found at these impact craters? Would there be enough time for life to form?
Yeah, so we're doing some modeling work to better constrain this, but our best guess right now would be perhaps a few hundred years, maybe as much as 1,000 years. We don't really know how much time life took to take hold on Earth. So this is something, I'd like to know more about. How far can you get towards life, given all the right ingredients, in say 500 years? Can you form life in 500 years, or how far along that path do you get? So this is something we're hoping to learn from Dragonfly.
I think there's also the possibility, to find something in an unexpected environment. For example, we have on Earth the ice worms. So you don't necessarily have to have the liquid water, but you can find, in theory, all kinds of organisms in all kinds of weirdo environments. So I'm really...
You do need liquid water for life on Earth. All life on Earth uses liquid water solvent. Yeah, they're very...
Right, but I'm saying that after that, it can propagate into all kinds of strange environments, and I'm really excited to see the possibility of this. And in that sense, I'm a little disappointed that you will land in the middle of nowhere, not some extreme environment. But I understand that for safety reasons, you have to do that. Erin is asking a question about how long will the Dragonfly mission last. I was having the same question. I think the battery will have as the main concern. Or not the concern, sorry, the main constraint for the length of the mission?
Probably. So the MMRTG, our radioisotope power source, will last for ages. The Voyager missions I mentioned that launched in the late 70s are still operational with their radioisotope power, 50 years later here. But my guess is maybe the battery will stop working at some point. Our nominal mission is several years long, but I really hope we can get an extended mission and keep flying around and exploring Titan.
Right. Since the atmosphere is pretty dense, probably only the bigger impactors will get down to the surface. Do you have a rough number of what are the smaller, well, not the smallest like pebble size, but the smallest like big impactors? What are the sizes for those? And also Dr. Riose had the question of how long roughly it takes for these craters to erode on the surface. The winds are pretty low on the surface, so I'm not sure whether it's the wind erosion that destroys them or is it the precipitation.
Yeah, so this is actually, I've spent the last 10 years studying these issues. So the most craters on Titan are larger than 20 kilometers in diameter. If you get smaller than that, they tend to break up in the atmosphere. So we see much fewer that are smaller than that. But even for the larger craters, we see a surprisingly few number of craters. My graduate student, Josh Hedgepeth, did a final count of craters on Titan at the end of the Cassini mission, and we came up with something like 90 craters on a world the size of Mercury, which is a very small number. And so we think they've been eroded, some of them beyond recognition. We don't know exactly how long that takes, but guesses on the surface age of Titan put it somewhere in a few 100 million years old. So, so probably they erode over hundreds of millions of years to the point where we can't see them. I have some other ideas for why we don't see craters on Titan. One of them being that they formed in a liquid environment. And we know that craters on Earth that form in shallow liquid deposits don't produce your traditional bowl-shaped crater form. You just don't see them. The only reason we know they're there is because we have drills on Earth and other sophisticated geophysical equipment where we can detect buried craters, but we don't have that for Titan. So if they are there, we wouldn't see them.
All righty, Brian, are there any other questions online?
Yes, they're in the chat.
I think I answered all of them, didn't I? Oh, sorry, not answered, but asked them.
I see one about, will there be any autonomous flight?
Oh, yeah, sorry, I missed that, yes.
Yes, I believe there is some LiDARs on board to help us pick a safe landing site, not unlike Perseverance had on Mars. And most of all of our flight is autonomous. So there's no operator back on Earth flying it around, since the time delay between Earth and Saturn is something like 2 hours. So yeah, we'll have a lot of autonomous flight going on Titan. And then there was a question of, will Dragonfly have an orbiter to beam data back to Earth? No, actually, we don't need an orbiter. We can talk directly to Earth through our antenna there. And that's part of the reason we had to land where we did. You couldn't land near the North Pole because it's pointed away from Earth. You wouldn't be able to talk to Earth directly. And this is one of the reasons that we could fit Dragonfly into the cost cap for the New Frontiers mission. If we had an orbiter, it would have been much more expensive and we wouldn't have been able to propose to this opportunity. So we had to have the direct Earth communication on board.
In the meanwhile, there's another question about potentially lightning on Titan to provide the energy to build the amino acid.
So we think lightning on Titan is extremely unlikely, primarily because methane, unlike water, is not a polar molecule. So it would be very difficult to build up a charge in the atmosphere. And certainly we haven't seen any evidence for lightning from Cassini. However, there is a lot of energy in the upper atmosphere, both from ultraviolet light from the sun and from charged particles coming from Saturn. And so this is more than enough energy to break apart the methane and nitrogen there, and then have them recombined into these much more complex organic molecules. So that's step one. And then once you expose those complex organic molecules to water, they very readily form amino acids. So a lot of the interesting chemistry is happening in Titan's upper atmosphere, and then it settles down to the surface where additional reactions can take place.
There is a question from James Robinson. The nominal mission shows an equatorial landing. What kind of specific mission range or distance per flight are possible with Dragonfly?
Right. So each hop, we can go tens of kilometers. We have the opportunity to do smaller hops as well, but we'll be doing larger hops on the order of tens of kilometers. So, you know, over the course of the mission, we can go hundreds of kilometers, if not more. It is pretty incredible, given, you know, this is probably the distances you're familiar with on Mars that are quite a bit shorter than that, because it takes quite a bit more time for those rovers to roll over the surface.
I think it's also exciting because you can investigate a very diverse range of phenomena and then study different kind of things and not just your local environment.
Yes.
So it's very cool.
Yes, exactly. Yeah. So we'll land in the sand seas, but then we're going to quickly make our way over to this really complex impact crater, which is a completely different environment. So we're very excited by that.
I guess you are very excited about that.
I am. Yes. I mean, I spent my whole career.
Oh, that's fine. That's fine. I understand. There's a question from Christine Mills. Did you simulate flight in Titan's atmospheric conditions?
I'm not sure if we've done a full-up flight model, but we do have a very large Titan chamber at APL that they're doing lots of different experiments at. So we have a chamber that's, you know, a human could fit inside, that's at Titan's atmospheric pressure and temperature that we're doing lots of experiments in right now. So I'm excited to make use of this chamber whenever the engineers are done with it.
Right. I hear you. I was going to ask what instrument or what type of experiments you are the most excited about, but you gave it away that it was the seismic data. So then let me ask this. Would you care to give some sort of a prediction of what will be a really exciting result or finding that will come out of this mission?
Sure. So actually, I'm probably most interested in the data coming from DRAMS, which is the mass spectrometer, because this will be our first opportunity to get a detailed chemical analysis of the surface of Titan. And if we were to find molecules that are consistent with biological molecules like amino acids or nucleotides, I would be very excited. And then if we were to find some sort of, you know, chirality to these molecules, like we're only finding one chiral form and not the other, that would be very exciting because that is indicative of life. And then if we were to find an isotopic ratio, you know, where you find more light carbon than heavy carbon, you know, that's another indicator for life. So that's what I'm looking forward to, is all these detailed chemical analyses and whether or not we can find structures and features that are consistent with biology.
Right. There is a question from Jack Chen. Is there possibility of Titan's internal energy contributing to creating these amino acids?
Probably not at the surface, but as I mentioned, Titan actually has this subsurface ocean beneath probably around 100 kilometers of ice. And that certainly would be warmed by Titan's interior. And if any of the organics on the surface made it down there, maybe through a very large impact and mixed with the water there, then perhaps there's another origin of life possible on Titan in its deep subsurface. And that certainly would be supported by its internal energy.
We have time for one more question if there's somebody out there who wish to ask Dr. Neish. Going once, going twice. Really, really the last chance, really the last chance. All right. Well, I would like to thank you again for the presentation, and I'm pretty sure that our audience out there really appreciated it. Our next science lecture will be on February 25th, and I will send out an announcement again about the topic and the presentation, the time and place, most likely in the same format. Did I miss anything? Probably not. Thank you again, Dr. Neish, and I hope to see everybody at the next lecture. Good night.